Hi everyone, welcome to the second week of the exciting conference. It's a great pleasure to have Professor Gopakumar from TIFR Mumbai. You already have heard him speaking on the first part on gravitational wave analysis and data analysis part, theory observation part. Today he's going to give his the second part. So Gopu, please take it in.
Thank you, Subhendra. So we are in the same department, so it's so he's going to give me more time. I may not need it. Okay, so if you remember, I hope you had a fantastic weekend in Mysore and Bangalore and other places. So I'm going to refresh your memory. We talked about the working principles of gravitational wave observatories. We kind of started from, linearize Einstein's theory, assuming the wave equation. We went on to show that there are two polarization states, and it's possible to define this critical coordinate system called transverse traceless gauge. And we considered particles there, and then tried to explain how actually LIGO observatory works, and even went on to argue that why you need Fabry-Perot cavity and things like that. And the argument that the LIGO is actually not measuring length differences and things like that. So I'm going to continue that same argument, but go to the next observatory, which is of course there in your poster. That's the LISA. And then I will kind of talk about a bit more about LISA, because I see many of your interests are going to be either detected or constrained by LISA and pulsar timing arrays. I will go into those. And again, I have not figured out many of these things. This is all from the lecture notes and discussion by people like Gerhard Schaefer, Lamont Saal, Strawman, Bernard Schultz, Bala Iyer, and many others. So I'll try to give a slight, slightly different to what you are familiar with LISA and others. And again, this is the disclaimer. Okay, so LISA. Well, this is an amazing, that actually stands for, as you all know, laser interferometric space antenna. And it's going to be launched somewhere next decade. So, and it consists of, you can see that this is Earth. So this is Sun, this is Earth. It's parked behind Earth, and it's an equilateral triangular configuration. The arm lengths are going to be something like 2.5 million kilometers. And so these are independent spacecraft. And again, in our discussion, we can fairly convince ourselves that these are going to be those free particles in the transverse traceless gauge. That's a challenge, which I'm not going to talk about. How to make, those spacecraft essentially a free particle. It's an exercise itself. It was so complicated that the IISER decided to have a pathfinder, so that you won't need to demonstrate that indeed you can actually make a spacecraft as a test particle. And this was very successful for various reasons, and that happened actually fairly along the same time as the first discovery of LIGO and things like that. Anyway, so the important thing is that it's an amazing, I will say, gravitational wave observatories between 1 and 10 millihertz. And there's a reason why I said observatories, but not independent observatories. Doesn't matter. And it may very well happen that in the next decade, there may be a companion to LISA launched from our colleagues in China. And unfortunately, I don't know much about it, so I'm not going to talk about it. And they are yet to decide which one to go. Okay, so that's the mission, as I told you. So that's the spacecraft you're talking about, our free particle for discussion. So, as I told you, this is 3 independent spacecraft. They are in an equilateral triangle. They are parked behind the Earth, fairly similar to JWST in that sense, not in a Lagrange point. And the laser beams, will be passed between the arms. And I just want to make sure that don't get the impression that it's getting reflected back from the spacecraft, because by the time the laser beam reaches the other spacecraft, it will be a kilometer or more wider. So there are more complicated ways to deal with it, which I'm not an expert to talk about. But I just want, if you're interested, go and read about those things. I had done it earlier. I can't reproduce it for the time being. Okay, so again, the spacecraft are essentially point particles following geodesics. I can bring in my TT coordinates to explain how it actually works. So, but if you have 3 arms, you can imagine that I can create 3 independent L-shaped interferometers. Can you imagine that? So it's something like this. Again, my drawings are horrible, but it doesn't matter. So this is one L shape. So if I call A, B, and C, you can see that A and C can form one L-shaped interferometer, not orthogonal, doesn't matter. This is A and B will form another one, B and C will form another one, and that's important, and I will kind of briefly talk about that. So essentially from arms that join at any 2 of the vertices. However, so these interferometers therefore are sensitive to, because the gravitational waves have only 2 polarization states, so you actually can, look for the 2 independent polarization states just by using one LISA. Since these days we talk about, gravitational wave background, you need to be careful too. So if you take any 2 interferometers, they share a common arm. Therefore, the noises are similar. Therefore, don't you dare to do this kind of cross correlation that we PTA people are doing. Should not be done. I'm sure that people are going to do it. So it's not really advisable to do a cross correlation experiment between the 2 detectors. So essentially to look for the gravitational wave background, but there are ways to do that too, and we will talk briefly about it. I'm not an expert again. I'm just going to give you a flavor which you might not have heard from, most of the LISA talks. Okay, and I kept telling you about most of the gravitational wave observatories. The sources are self-gravitating objects, compact objects, so they are in binaries, so they follow omega square r cube is gm. I rewrote that, and if I look for the peak frequencies when the r is going to be the last stable circular orbit, then essentially the peak frequency will be given by the scaling law, 1 kilohertz times 10 solar mass divided by m. That's the total mass of that self-gravitating system, and that's essentially what I need to explain this diagram. So if you're going to use stellar mass black holes, you will essentially see the merging stellar mass black hole or neutron star binaries. That's what essentially we are seeing with LIGO-Virgo-Kagra collaboration. And if I'm going to move that into kind of a million solar mass black holes, I will end up seeing the merging supermassive black hole in the LISA bandwidth, and that's what the excitement all about. And you will actually find this relation can be used to look for non-merging stellar mass black holes too, and that definitely will be done, and I will go into all that. But you can see that they're also going to see the background, not from the kind of background we talk about in PTA. These are because we know there are stellar mass binaries in our galaxy, that there are too many of them, and they're actually going to form a background at low frequencies there. These are by wide dwarfs. By the way, when I say compact object, in the case of LIGO, that's essentially neutron stars and black holes. But for LISA, we have one more guy that's wide dwarf binaries. They're all supported by degeneracy pressure. They're still compact. They're slightly puffed up. Doesn't matter. So that's the, I'm just trying to give you that flavor, okay? And you can see there are interesting sources here, and I'll come into that from a slightly different perspective. So extreme mass ratio in spiral, and we'll talk about all that. And then I'll get into, why I'm talking about that, because this is the one we expect to see. All unexpected sources are interest to many of you here. So hence, just want to tell you what are going to be expected so that you can distinguish unexpected sources, which are going to be, critical to make LISA the JWST of, gravitational wave astronomy. Okay, so when you are going to deal with black hole binaries, I'm going to put a figure with this. You're fairly familiar from your, one-body problem, the Keplerian one-body problem. I'm going to make it slightly complicated, that's all. This is the paper, this is from a paper, I wrote with Bala Iyer and Thibaut Damour. So this is essentially some sort of a radial potential as a function of some scale radial variable. It doesn't matter what those are. And the plots are for some angular momentum. What is important is that what LIGO these days seeing are this binaries which are here, I marked at C, that's the circular orbit. So that's just the point. And what LIGO sees is binary when it in spiral, this potential becomes like this, and this point will be there, and that plunges and you get your merger signal, okay? That's the way you should think about. This is just one snapshot of that. So this is one part of the binary, and when it evolves, it goes to here, and then in the case of LIGO, what you see in this point will become, that's called the unstable circular orbit point, and then it just merges, okay? But this is very important. You can see that this is an eccentric orbit. It's still, this is the effective potential, so you can actually turning points here, and you can see that, so you'll have two turning points, that's eccentric orbit, okay? But you can have a fantastic configuration here. You can see that this point touches here. This is what you call the stable circular orbit, the last circular orbit possible. But you can see that there's sufficient energy that you can actually consider a configuration that you come here and it still doesn't plunge, okay? And that's something called extreme mass ratio in spiral. I'll go into that in a minute, but just keep this figure in mind to show that the LISA will have fantastic types of binaries where they probe GR at very different time scales and length scales, okay? Okay, so, and I told you again, I just keep repeating that to you. What are the sources? So again, if you have peak frequencies, you can argue that LISA will see gravitational from supermassive black hole binaries with the total mass somewhere in the range of 10 raised to 5 to 10 raised to 7 solar mass. Those are the galactic, these are the supermassive black holes that we are familiar. In the galactic center is 10 raised to 6. And then there are nearby places where you see somewhere in this. So if such a binary kind of merges within the lifetime of LISA, you should be able to see it wherever it happens, essentially very high redshift, okay? But it should happen within the lifetime. That's very important. And it's more exciting. So what happens is that this can last for months depending on where we got captured, depending on the sensitivity of the LISA eventually. So, and the total masses and all that. We should be able to see, you have seen the LIGO signal, right? It has in spiral and the merger. The in spiral part will be there for months. Therefore, you should be sufficiently able to tell your electromagnetic astronomers that something going to happen in that part of the sky. May not be arcs minutes or arc seconds, or it may be square degrees, but that's fine, because once you are telling electromagnetic astronomers to look into some 10 square degree patch of the sky because there's going to be a supermassive binary black hole merger. I'm sure that every piece of glass will be looking at it. Okay, so that's amazing. And then electromagnetic observation can follow up, and you know what happens if you're familiar with 170817. If not, read about that. Okay, and why this is exciting, we should be able to probe growth, evolution, and initial mass spectrum of such supermassive black holes, and that's exciting. And here, these sources are essentially a scale-up version of what we actually see in LIGO. So that's what I said, the orbits can be. So essentially, you expect binaries, essentially following this kind of trajectory. It can be either eccentric, circular, but during the mission, during a year of observation, this effective potential will sort of sink and you find the merger ring down and all that, okay? Essentially what you expected from LIGO observation, but more massive and different mass ratios and things like that. There may be spins and processing and whatnot, but pretty much everything you have seen and the mass is just a scale in GR. It doesn't give you more. Of course, astrophysically very different, but from a GR perspective, your numerical relativity simulation can just be moved over to LISA. Nothing going to happen, just a scale. Okay, good. When I said those things, if you're not following it up, ask me or read about it. Okay, good. Now there's the other guy. It's called extreme mass ratio in spiral. So what happens is that we know, well, it's actually because of Subramaniam Chandrasekhar that if you have compact objects in our galaxy, so like stellar mass black holes, they experience something called dynamical friction, which sort of force them to go to the galactic center. Okay, how that works, it's actually fairly beautiful. It's it's a half an hour lecture, but it's this is what Chandrasekhar figured it out, not for black holes, for other things, some close to 80 years ago, something like that, right? Second passion. Okay, so there will be an overdensity of stellar mass black hole near the vicinity of supermassive black holes. So is it possible that some of these compact objects kind of interact with each other? There's a huge amount of astrophysics there, and they essentially get thrown into the supermassive black hole. Okay, and so this is essentially on a plunge orbit. It's directed at the supermassive black hole. So we are not talking about S stars, which you are maybe familiar, where we actually see the stars in orbits which are just 10 years near our galactic center black hole. It's much more relativistic. It just goes in directly aimed at the supermassive black hole, and most likely highly eccentric. And that kind of orbits we are very much interested, and that's called extreme mass ratio in spiral, because the mass ratio will be 10 solar mass compared to 1 million solar mass, hence the extreme mass ratio. And if the impact parameter is sufficiently small, for example, S stars, that's not the case. The first pass black hole should radiate, so you go in, it's a plunge. It's so like you can imagine this as a hyperbolic orbit. So the hyperbolic orbits goes in any figure harder. So you can, like this. So this is your total M, and this is the black hole. It's a relative coordinate system. So you can this is open orbit, like Oumuamua, for example. Have you heard about Oumuamua? Please read. It's an amazing thing. Okay, so eccentricity can be 1.4 or whatnot. So it's but if the impact parameter is sufficiently low, the gravitational wave emission can take away angular momentum. It can make an eccentric orbit. Okay, and that essentially conversion from hyperbolic to eccentric. Then what happens is that there can be a large number of orbits where this perihelion, instead of perihelion, the word is periholon distance remains roughly constant, but the upholon distance shrinks. Okay, and this kind of events we should be able to see up to maybe a fraction of a redshift. And there can be up to 10 raised to 5 orbits, okay, of, these guys. And I'll show you how that looks like. Unfortunately, I didn't get time to kind of put a plot which is convincing to you. So there can be 10 raised to 5 orbits before that stellar mass black hole plunges onto this, LISA, into the supermassive black hole. And therefore, we should be able to actually compute or probe in detail how a supermassive black hole exterior looks like, because you have 10 raised to 5 orbits to look around for those, and test uniqueness theorem of GR. Essentially, the black holes are essentially given by mass and the spin, whether maybe black hole Noether theorem and things like that. But provided we know how to compute the waveform, and it's a tough task. We don't have those waveforms for the time being, and that will be done. So what I meant by is that this is what I was talking about. You can see, I'll just go back. Yeah, so the orbit I'm talking about, this is the upholden I was talking about. This is so there is this unstable circular orbit. It comes there, it can move around there, and again go back. And it's called Zoom orbits and things like that. Essentially, those are details. I just want to give a geometric feeling. So it's very different from the kind of orbits that we see from LIGO observations. So this distance will shrink because this guy is also shrinking. This effective J is also coming down, but there are 10 raised to. So that actually prompts the geometry of the black hole very close to last stable orbit. That's what I'm talking about, testing GR very precisely and all that, provided we know how to do this waveform in a computationally efficient manner, not doing the perturbation, and all that. It's a different question. But people may wonder, do they actually have such things possible? I mean, and by the way, I just want to show you that it's also, you can see that these are the huge supermassive black hole I talked about, and these are, and I will come into that, resolved galactic binaries. You can see that there are too many of them. And this LISA, extreme mass ratio in spiral, is pretty low. So you have to remove these foregrounds or whatever you want to call them and get those things. It's not going to be easy, but it will be done. And unfortunately, if it was 5 million kilometers, things could have been much better. Those are beyond our control for the time being. Okay, good. Okay, so the question is that, do they actually happen? We have S stars, but we are not interested in S stars. But these days, we suspect that such things are happening. So what this cartoon is actually based on a Nature paper which came out recently last year. So people have seen something called quasi-periodic eruptions. Okay, so what theorists or astrophysicists are thinking so there was a black hole here and there was a star which came too close to it. Okay, it got disrupted, and that's called a tidal disruption event. It created this accretion disk, which is fairly dynamical. And the claim is that we most probably are seeing a black hole which plunges through this accretion disk and giving out X-rays. And we have been seeing those quasi-periodic X-rays, and this is getting a lot of attention these days. To best of my knowledge, there's something like 6 Science Nature paper for the last few years, with our very good X-ray facilities, and that's exciting. So it actually shows that indeed what Chandrasekhar theory told, that there should be black holes near the galactic center of supermassive black hole, are true, and they are even interacting with material which are created by tidal disruption of normal stars. So those students who are interested to work in MRIs, this is their real motivation. And this scenario you'll come across in another talk, but that's for later. You can read this beautiful article, which is, anyway. But yes.
Actually, on the slide before this, for gravitational waves produced from extreme mass ratio in spirals? Am I supposed to be imagining bursts when the black hole is at its distance and closest approach?
Yep. So,
and would Lisa see bursts, or would Lisa see the stochastic integral?
Okay, good question. So, if you are looking for the burst which created such hyperbolic to eccentric, we may see one burst, because the time for the next guy to come back may be beyond the few years Lisa may be operational. We saw for a decade, maybe. So that's another thing. And the orbits we are going to see are not just the perihelon passages. When you go to the perihelon, you essentially get localized into that unstable circular orbit region. So you actually go around making several cycles there and then go back and then do all that. So this is this, Sumbril orbit I'm talking about. Thibaut, that figure by Thibaut Bala, I think is the easiest way to explain that. That's what I was trying to do. Does that make sense?
Yeah.
Excellent. Okay. Okay. But there may be other possibilities, and this is why, and this is bordering to what you guys are planning to, look for in LISA. So we can also think about intermediate mass ratio in spirals, where it's not the stellar mass. You're talking about a 1,000 solar mass black hole, which we have not technically seen, right? But they can actually come from population 3 stars, and most likely JWST is pointing out to those things. So there can be, black holes whose masses are somewhere between hundreds to thousands solar mass black hole. And Chandrasekhar says that they also will have to go to the galactic center. They will have to, it's difficult to kind of plunge them into an Emery orbit, but it's possible, who knows? And if they can be captured by a galactic supermassive black hole, just like the way I just talked about now, we are in for a big treat. And unfortunately, we have no idea how to compute those waveforms. But that's the challenge. Numerical relativity cannot help you because the mass ratio of 100 and you need 1,000 orbits, forget it. And perturbation theory. Yeah, but I showed you in that. That's again, so when you talk about beyond standard model, new physics signals, you are going to compete with many of those things. I just want to give you that flavor. But no, this is an exciting data, and the data is not that big. You can actually carry it in your iPod or whatever. So, can be all done eventually. So, but the data stream will be dominated by binary systems within our galaxy, and that will be essentially compact binaries having wide dwarfs, neutron stars, and stellar mass black hole. And more importantly, there is another thing which have not been taken into consideration or attention. People are going to look into that carefully. Square kilometer array will be operational by that time, in 10 years' time. And we are going to see, pulsars with companions which can be either black holes or neutron stars, like the neutron star binaries. And if they have orbits which are slightly less than 2 hours, you should be able to see them as a persistent gravitational wave source. So you already have SKA seeing them in electromagnetic window. These are giving them gravitational wave signal, and it can have fantastic ways to measure moment of inertia. You should look for upcoming papers and those. And why I'm talking about that, see, this is, again, you should read about this. It's a beautiful system. This is 2 wide dwarf binaries with an orbital period of around 8 minutes. Wide dwarfs are roughly compact objects size of the Earth, and they're going around each other once in 8 minutes. That's fairly extreme, and you can see that. That's the guy. They're kind of pointing it out there in the red. Okay, so so when LISA, they turn on, if you don't see this guy, the mission is a failure. Or the GR is extremely wrong. That's highly unlikely. Okay, so this is so strong. You can see that. This is your noise curve, the wave in a strain. Right? So we are just having few of them. How many? We have no idea. electromagnetic surveys. CTF is, Circuit Transient Facility. So that's essentially that. And you can see that people are actually using this to test the general relativity by the gravitational wave emission. They discovered it somewhere here, but they went back to archives and then looked for data. Again, something similar to what I do for fun, but we'll talk about that later. Okay, and since I told you, if there are objects like pulsar binaries, so this is double pulsar, famous two of them, it's actually probing GR most precisely at the quadrupolar order than anything even LISA can do. Okay, so again, that's one. But many of you are interested in the stochastic background created by, beyond standard model scenarios, and LISA will be able to do that in the sense that if there's a stochastic gravitational wave background, you should be able to see it, because it's not that as a great scenario like in the case of PTA, but you should, provided the noise is higher than the instrumental or confusion noise. I told you the confusion noise is that in the galactic scenario there are too many wide drops. See, I already showed you, these are the electromagnetic counterparts we already seen. So, and electromagnetic scenarios are, it's just, so how many are there in the dark sector? Nobody knows. Lisa will tell you. So the background, we need to be careful. And what's a good thing about is that if the gravitational background, either astrophysical or beyond standard model scenarios, give you some, and if it's higher than the noise level, is higher than the instrumental or confusion noise from on the also foreground and solar winds and all that, you should be able to see it. But important thing is that, and I will just briefly talk about later, that LISA output, because we have three such configuration, we can create something called time delay interferometry. There's a mode, it's called Sagnac mode, and that the gravitational signal will disappear. All is the pure noise. So if the LISA output noise, the original LISA noise, is higher than so-called Sagnac noise, but no gravitational wave signals are present, then you can claim we have detected a gravitational wave background. So again, I'm not an expert on any of this, and we will talk about, I'm sure that, there are experts in many of these in India, and I'm sure that some of the youngsters will learn from them and all that. And then unexpected gravitational wave sources, that's precisely what you guys are interested, individual or otherwise background. So, why I'm saying this, because I thought I will focus on LISA, and I just want to, get a bit more time. I don't have much of the slides. Okay, good. Now we'll go back to, so that's the motivation for the youngsters to work on LISA related efforts. So again, we go back to our previous lecture. We tried to do this very elementary analysis and showing that the proper length between freely falling particle are essentially given by x0 lines. So we talked about one at the origin, one at this spatial point x1, xyz coordinates, and so these particles remain frozen in these coordinate points at the origin as well as here. And we showed that the passing gravitational wave will change the distance measured by the metric given by this expression, and this is essentially this elliptical deformation that I talked about and I showed, induced by passing gravitational waves. Okay, we will start from that. So LISA now going to be a toy model for us, just to get the feel. Okay, again, I did not discover any of these. These are all figured out by masters. I'm just reprocessing it for you. So let one half of the interferometer be the x direction, and our gravitational wave is plane in nature, so I don't have to worry about x component or spatial component. So gravitational wave as usual is moving in the z direction. I'm going to restrict to the plus polarization. I want to make my life as easy as possible so that I don't have to worry about details. In that case, obviously you have null geodesic to deal with. So this is the expression for that. Essentially, we derived this. You can go back the notes and find that. I can obtain an effective speed that goes like this. By the way, h plus or h cross, whatever, it can have plus or minus. So, but you may wonder, there's a c here. I just removed that. So this is a coordinate speed. So you're perfectly all right. We are not violating special relativity. And so now we'll consider a photon. Again, we are not measuring distances between those spacecraft. I just want to be very, very thorough about it. We simply don't have the technology. The photon is emitted at a time t from the origin, and it reaches the other end at a fixed coordinate position L. And then we can just use this equation, elementary, just obtain the t for the other arm given by t plus 0 to L integral given by this. And I just want to emphasize that t of x is important. It's the fact that you should know the time to reach the other mirror, other spacecraft, to calculate essentially the wave field, which is what I'm going to use on the way. Okay. So, of course, I'm not going to talk about square root of half. That's because it's all linearized for the time being. This is the expression I get after that. So, in a space interferometer, light is essentially reflected back. That's a very, very scary statement. It's not like using mirrors in the Fabry-Perot cavity and all that. None of those. It doesn't matter how that operates. It's a kind of a sophisticated way of receiving and then emitting and all that. So you can essentially, I look at this spacecraft, send something out, and I get a reply from the other guy. So that a t return time is essentially given by this integral. It's elementary. Just added that L here. Just calculate those fields at those points along the path. Okay, I'm integrating along my photon trajectory. So, and I'm not going to measure any time. What I'm going to look for changes in my return time, because that's what's going to induce the phase problem for me, phase differences. So essentially, a gravitational wave observatory, which is in the space, I am essentially going to monitor changes in the time of return trip as a function of the time. Again, this is for to get that basic idea, not the gory details here. The reason why this is that the spacecraft itself is tumbling. The configuration moves around the Earth, and which essentially follows the Earth around the Sun, and that is a complicated trajectory. And also the entire configuration has to tumble. There's a certain rate for that, and the Earth, the trajectory around the Sun is eccentric. There are perturbations from other barycenter, and all that. So all those things goes in, but I'm not going to talk about any of those. So therefore, when you do that, I can just do I take this expression, take a differential, and that's essentially dt returned dt, and this essentially gives that. But in general, it becomes a bit more complicated, because you can imagine that the wave travels at an angle theta to the c direction, not exactly along. Then you get a slightly more different. You should work it out. It's kind of interesting to do this. So, but you can everywhere. The problem is that we need to know, how this x, which I talked about, kind of hidden in this. We need to know how to incorporate all this. In this case, it was the h11 or h22 kind of thing. So we need to know how it depends on the x coordinate to get that expression. Anyway, but in reality, this is essentially the working principle of LISA. This will induce the phase differences, which I will, can be picked up and all that. But it's very complicated than that. This is essentially a theoretician's way of analyzing LISA output. You can see that, it's actually from a paper by Kurt Cutler and his collaborators. And Kurt actually had this paper, how to get the response of LISA for practical data analysis and all that. People use that. It's essentially stolen from that. So you can see that this is L1, L2. So one of the arms changes. You can see that and you can see the Hij projected onto those arm lungs and all that. And the second orthogonal signal, you can see this. You will see this is that the cos 60 will come in square root of 3/2 or something like that. Those things are all hidden here. And then because there are also square root, that's essentially because you have 60-degree scenario. Okay, and then because it's all messed up. It's huge number of terms and cosines and whatnot, and you can see. I think he did not. You can see here that capital T is 1 year, and he assumed a circular orbit for the LISA center of mass around the sun. That's actually not the case. One should worry about the eccentricity. So analysis gets much more complicated. So, and you can see that's all Cutler and his collaborators' papers. I just stole it from one of those papers. Just want to give you a flavor. Yeah. So, but when you do all that, people have done many of this analysis, usually in something called Fisher information matrix. Is assuming high signal to noise ratio. You can do that to extract kind of parameters, how accurately I can do that, and shown that many of the sources I listed, you should be able to get a fraction error in the chirp mass and maybe mass ratio and things like the spin parameters and all that. So that's a scenario I'm talking about. Okay, good. So I just, on the way, I will just pass this. So as I said, it's around, the advertisement is that it's a good interferometer from 0.1 millihertz to 0.1 hertz. Operationally, it will be much smaller, but it doesn't matter. You will still get plenty of signals. So as I told you that it's a combination of 3 LIGO kind of interferometers. So you can actually have, it's possible to create a configuration where the gravitational signal vanishes. It's called time delay interferometry. It's a fairly algebraic geometry involved to extract these things. It's a fantastic thing. So essentially that's called a Sagnac mode. There will be no gravitational signal. You can create from these 3 interferometer a combination. The signal is not there. And that's precisely what the data analysis person wants, because what you have is pure noise. So you can characterize your instrument, calibrate it to perfection. And it's a very challenging. We have not demonstrated this on a mission. LISA Pathfinder did not do it, clearly. There's not even interferometer there. And this is something one of the pioneers of gravitational wave astronomy in India, along with Professor Bala Iyer, who you will be meeting in the coming days, somebody called Sanjeev Dhurandhar. He pioneered gravitational activities in India, and Sanjeev has written a beautiful review. And I am interested, but I don't have I'm trying to slowly learn this, because it should be possible to adapt this for pulsar timing arrays, because we also have many arm interferometers, right? Sanjeev thinks that it should be possible. We need to spend time, but we'll see. Okay, and that's a good way to get into PTA. So I just want a connection. So do we have any questions here before I jump into that? I would not last 11 o'clock, so yeah. Yes. Come again? The rotation of LISA. Oh yeah, oh yeah. So I actually showed, the rotation of the LISA, because it tumbles, it's not even rotating, it tumbles in a very specific way that goes into the, the way the effective strain is computed. And this tumbling, and also it goes around the sun. So both needs to be incorporated, and the TDI works only when certain long wavelength approximation holds, it's a mess. So it will be fairly restricted to certain frequency ranges, definitely not 0.1 hertz. I don't think it's going to work on 0.1 millihertz. I'm not so sure, but there's a sweet spot where it should work. And without TDI, LISA mission is also going to be in jeopardy. So I hear that there are developing backup plans, to do this kind without operate LISA without that and all that. So yeah, it's a mess. I am not an expert, so I read, but that's only reading. So. Okay. So youngsters, please, you still have a lot of time. So. Okay, so we are in a position to go into nanohertz gravitational wave observatories. And that's the cartoon for that. I think I stole it from Maura's, she gave me all this. So this is, okay, so pulsar timing array. So we have seen a terrestrial based gravitational wave observatory. Then I moved into solar system based gravitational wave observatory, one of them. Now the third one is the galaxy sized gravitational wave observatory, and that's the one here. So that's the galaxy, the space-time of the galaxy perturbed by this massive black hole binaries and phenomena coming from beyond standard model cosmology or particle physics, it's perturbing the space-time curvature of our galaxy, and we have this fantastic prompts. These are the pulsars in our neighborhood up to a kiloparsec. And we are using them to look for gravitational waves, and we have made some interesting advances. Okay, so before that, I want to talk about millisecond pulsars. I'm sure that many of you are familiar. Again, this is for the youngsters here. So essentially, a millisecond pulsar is it's a rotating neutron star. So it's a compact object, and it was discovered by a graduate student. Before I was even born, so that doesn't mean it's fairly old, but not ancient. So Jocelyn discovered it in the late 60s, and essentially a millisecond pulsar. This is a neutron star, roughly the size of Bangalore, but it will weigh something like 2 solar mass, and it's rotating with a rotational period of milliseconds. So you have to imagine what is a millisecond, right? 1 millisecond is what I think there's an advertisement recently that some of the dragonflies will move the feathers by some 20 times or something like that. So that's a millisecond, So and these guys will have close to 1,000 millisecond rotation in a millisecond. So. And therefore, its moment of inertia is highly stable. So it's almost a ideal rotator, and it has a beam of radiation. We can track that beam using some of our best radio telescopes in the planet, like our own upgraded JN meter wave radio telescope created by Govind Swarup. So the stability of this neutron star clock is comparable to stability of atomic clocks if you are willing to wait for a year or no. So if you take an atomic clock and compare with a millisecond pulsar for a day, you will say no way. But if I can monitor millisecond pulsars for years, then their stability is sort of comparable to atomic clocks. That's the key point here. Okay. However, and how do I do all this clock business? I measure the pulses using radio telescopes. But in reality, it's very, very different. These pulses from millisecond pulsars do not arrive at constant frequency on any of our telescopes. We have to create them an Einstein clock out of the data, because the pulse time of arrival, that's our observable, are affected by many, many effects. So the pulsar, the observatory is on Earth. Earth is moving around, it's rotating, it's moving around the sun and whatnot. And then the pulses are actually passes by gravitating objects, either in the solar system or in the vicinity of that pulsar, and then these are electromagnetic pulses. They will get dispersed and scattered by interstellar medium. All this needs to be taken care. And we have developed so-called what we call as the deterministic timing formulae, class of them. One by Damour and Derwell is the classic one for binary pulsars, to ensure that all kind of delays which are caused by, effects we can think about, and people are very smart. Thibault is a very smart guy, Roger and many others talked about all that, and we can actually take care of them if you regularly monitor millisecond pulsars for years. So anything which are deterministic, we should be able to correct for the multiple observatories, multiple frequencies and all that. We are very good at it. And therefore, we are able to predict time of arrivals of close to 100 millisecond pulsars. We have not detected more than few hundred. See, something like 3,000 pulsars are detected, of which 10% are millisecond pulsars which we can trust. So we are close to 100 thanks to mere time and fast. We have some and other big observatories. We have around 100 of them, and we can create a time series, what we call timing residuals. What we have is that using the deterministic timing formula and the pulsar data for years, we can predict when we observe the pulsar in the next epoch, when those time of arrival will happen today in the evening. Okay, but in reality there will be slight difference when we observe, and those are what we call pulsar timing residual. These are hundreds of nanoseconds for the time being, and then we can argue that a passing gravitational wave will actually change timing residuals in a stochastic manner, and we are trying to look for those. That's all PTA all about. Usually in a popular talk, I give lots of cartoons. This is not a popular talk, so I'm going to restrict myself to this. And these are essentially by Sachin, and then, I never read that paper, but I know this beautiful paper by Steve Detweiler, and essentially kickstarting the area. And Steve was actually S. Chandrasekhar's student, so is an amazing character. Unfortunately, passed away a decade ago. And Steve was very fond of Indian students and lots of stories to talk about. An amazing person. I actually had a chat with one of his students just before coming here. We are doing something together. Okay. Anyway, so, but if you are interested in PTS, this is the beautiful paper by Steve. It's very detailed. I haven't finished it myself, but Steve has done a fantastic job, and it's everything available required are there. Okay. Now I need to tell you how it works, and that I will do. Again, we go back to our the metric I talked about this. So we need to assume now the test particles are the Earth. Actually, solar system barycenter, it doesn't matter. It's Earth and the pulsar. Okay, we know how to do from here to there. So let's imagine that. So then I also have the linearized gravity, and I assume, I'm imposed already TTK, transverse and traceless. So I have no temporal components for this. My mu nu for regular talks were all from 0 to 3. Remember? So all the slides will be available. You don't need to take a it's fine. So, and then we demonstrated that if I consider curves where the spatial part is a constant, they are geodesics. World lines of constant spatial coordinates are geodesics. We demonstrated this. If that is the case, we argued that the h mu nu can be an arbitrary superposition of gravitational waves, and then this is the metric what we started here, because there are no cross terms, they all disappeared in this TT gauge, which I'm allowed to do in GR. So this is what it is. So along the word lines of pulsar and Earth, I can argue, because I'm talking about geodesics, these are the proper time. And that's required, otherwise I have to do a bit of nasty things. So we can identify frequencies with respect to time coordinate intervals, delta t. Okay, so both Earth and the pulsar. I mean, that's the easiest way for me to. So this is the diagram I will be considering. This is essentially lectures by Klaus and Gerhard and others which I have access to, so I listen to and. So you have the pulsar here, this is Earth, this is the origin. You can see that this is the constant spatial things I was talking about. This is the Ni, which is a unit vector which I defined using the Minkowskian background. So the pulsar emits signals at a fixed frequency here. The pulsars arrive at Earth with a frequency which depends on the Earth time coordinate, and we need to figure this one out. Again, I go back to my metric and I rewrite, and of course I have an arc length with respect to Minkowskian background, just given by this. So you have c square dt by dl square. This is what I get. And since I'm linearizing things, when gravitational waves are around, I can, from here I can say dx by dl is just ni. So I have an affine parameter to kind of play around with. So it's not that big deal to get this dt over dl as this expression. Not interested in square roots, I'm going to expand that, and then I'm going to integrate that expression for, dt, below expand and all that. So I get integral from Tp to Te, which is L over C. That's very straightforward way. L is the distance from pulsar to the Earth. And again, I'm assuming that measurements, I don't really care about any possible modification or propagation effects and all that. I differentiate that expression with respect to Tp. This is what I'm going to get. Again, I linearize. That's the reason the square root disappeared and half came in. So then I get dTp by dt as this expression. I can still expand that because I'm not going to keep ratios like that. When I do that, this is what I get, dTp over dTe as given by this. So the Ni, I told you, dxi by dl with respect to the flat background. And then, and once I have this, I can convert that into the frequency at the Earth as well as the pulsar, because delta t inverse is going to give me the frequency, proper time interval inverse of that. So that's because of the way I chose my coordinates and the geodesics and all. You can do this much more sophisticated, and Steve does that. So pulses which are emitted with constant frequency arrive on Earth with a frequency this, and I can compute that in a very straightforward manner, and this is what I get. And pulsar timing residuals are essentially integral of that. And you can see that, so the timing residuals induced by gravitational wave background, gravitational wave, I'm not talking about background here at all, just a gravitational wave will have a pulsar contribution as well as an Earth contribution. That's important. And of course, it depends if you have amplitude to Hij, which are projected onto Ni, and Ni in this case, in the XY plane, because I consider things propagating along the C direction. So those are all required, otherwise you get a, and that's essentially is that. Okay, so this is a critical formula, sort of a back of the envelope argument, not really back of the envelope, but based on, linearized gravitational wave solution to Einstein equation, linearized Einstein equation. So, and you can make it a bit more complicated if you don't assume the source to be along this gravitational wave along the C direction and all that. So this is what essentially Steve worked out, Steve Detweiler worked out. So you can see that alpha, beta, gamma are the pulsar direction cosines with respect to x, y, c, and I incorporated the pulsar and Earth term, and I put all the background gravitational wave polarization back. Then you get C like that. C remember that C is essentially this. Okay, you go into different, so here because this is coming from some other slide of mine, I just pulled it, it's a screenshot. Okay, so the observe and measure TOAs are compared with their predictions based on an appropriate timing model. The differences are called pulsar timing residuals, and this observable timing residuals are essentially integral of that. That's one can argue why this is the case, because it's a fluctuation of the, we don't know whether this pulsar timing residuals are happening because I have an inappropriate timing formula. And what does that mean is that and this affects, I have to, these are not instantaneous measurements, right? So I need a time series. So I integrate this fluctuation, and that's how I make a comparison. Technically there's no mathematical proof that this is what I observe, but it's more a argument. I mean, I haven't seen a mathematical derivation that this is the timing residuals I actually extract from, pulsar observation. I haven't seen them. Maybe I should think about how to do it. Anyway. Okay. Oh, by the way, this is signal. It is our symbol for Indian pulsar timing array. I'll come to that in another talk. Okay. So that's how pulsar timing array works for all. Yes. Correct. We talked about that in the talk. Yes. Correct. Precisely. You don't have to worry about that in the sense that, so you are asking about short wavelength approximation versus large. So it's kind of an optical, it's a geometrical optics versus, a wave optics argument. It doesn't really matter for the time being. This sort of matters if the source is too close. Because the wavefront may not be planar and all that. So for the time being, it's, the much more sophisticated thing is that if there is a companion to our galactic supermassive black hole, which emits nanohertz gravitational wave, how will it affect pulsar timing residual? That's a bit more sophisticated because we are not in the wave zone. Here I assume, because in electrodynamics, I have the near zone, I have the wave zone, I have intermediate zone and all that. We need exactly like that for GR2. In fact, all the templates we created, essentially thanks to Thibault, Blanchet and others, actually do many complicated things at the intermediate zone and all that. Anyway, so I don't think, I'm not really thought about that difference as such. You have comments? Go ahead. I have not going there. Somebody already covered. That's the reason yeah, sure, I know, yeah. Yeah. Agree. So the classic, even if you know the derivation of HD correlation, you still need to read Bruce's paper. He actually explains this why, these are not matching and all that is, and the quadruple nature, yes, but more, as you said, they are related to this approximation. So long wavelength, short, yeah. Okay, and so I don't know whether people covered this. I'm going to do that because Professor Mohanty told me that he will give the derivation of the HD correlation. I presume he did that, right? So that's the reason I am not going that way. Good. So what are the sources of pulsar timing array? As I told you, this is the cartoon for pulsar timing array. So this is the timing residual as a function of the timing data. So these are in years. So we are familiar, we are most probably sensitive to that first guy. You can see that the signal in the time domain looks like this. It's a kind of a slowly varying signal. It's not periodic. And if you take that's the way I think about it. If you take the Fourier transform of this, you will see the power peaking at the low frequency. Hence, we call it's kind of a red noise. So, and then we are expected to see continuous waves from individual sources. And we have something called bus, most likely with memory. So these are the sources. What does this even mean is that what happens is that the gravitational wave even passes by, but it changes the rotation of the pulsar to a slightly different value, okay? Because the space-time itself went into some sort of a hysteresis, if you want to think about that way. And if the pulsars are rotating at a slightly different frequency, when you try to integrate that, because the frequency has changed to, a slightly different value, and it remains constant there. So when you try to integrate over your time coordinate, you will find a thing which is linearly changing. So it's sort of different from the glitch, because the glitch will be individual, but this will be for all pulsars what you are dealing with. So that's the scenario. And why a background? This is something always asked, and I don't know if somebody answered that question. I'm going to repeat this, allow this argument. So, suppose imagine that the cosmological population of massive black hole binaries are going to give a gravitational wave background for the PTAs. So how do you know that? It's a background, not individual. So the game is that to look for how many sources are there in a small frequency interval. That's your resolution, which is 1/t observed. If the data is for 15 years, the delta F will be 1/t 15 years. We'll convert that into seconds, otherwise it makes no sense. Okay, so then that delta N will be dN/dF times delta F. I can rewrite that into dN/dt times dF/dt inverse by delta F. That's allowed. But dF by dt is what LIGO has measured, or binary pulsars have measured. It's actually the frequency chirping, characterized by that chirp mass and some power of frequency. So then, all I need to know is what is dN/dt. I don't know that, which is actually true. Nobody knows that, but there are ways to do this. But for this, we assume that, imagine there are something like a trillion galaxies in our universe, and the universe is going to last around, we know it's around 10 raised to 10 years, 10 billion years. So, and imagine that at least once in the lifetime of every galaxy, it goes and collides with a companion galaxy. So for example, Andromeda is kind of plunging towards us. It will merge with, and we assume also that if that galactic merger happens, collision of galaxies happen, the associate black holes also form, and they emit nanohertz gravitational wave. This is all huge assumption, but I need some numbers. So if I do that, the rate per merger of supermassive binary black hole in 10 raised to 10 solar mass kind of thing are roughly 10 merger per year. Okay, you can make a fraction of it, it doesn't really matter. And then I go and compute, substitute in that delta N expression I just obtained here. I have a number for it, and I can do the scaling and all that. And then if you put delta N, you should do this, and this is what you get. You get chirp mass, I normalize around 10 raised to 9. We can make it 10 raised to 10, it doesn't matter. Frequency, I'm putting around, 10 nanohertz or something like that. And observation is around 10 years. And the merger rate is around 10 merger per year. The number of binary black holes in that small frequency interval of nanohertz is 1 trillion. So you'll say, you are idiotic, this is not 10 merger. Yeah, fine, make it a 1 merger per million years. It's fine with me. I still are going to get many, many sources. Of course, you can say that this is 0, and none of those things happen, then it's of course 0. that if I make anything 0 here, it's going to be 0. But if I make it tiny, I will get few. That's the game. So, and this is what we get a diffuse background. And since I'm looking for background, my pulsar contributions are not going to be relevant. They are incoherently added. Anisotropy and other things are more higher order. That's something people are working, and some of my colleagues, I'm trying to learn from them, Raji and many others. Okay, so, and then once you have a background, you characterize by an amplitude and a frequency evolution. -2/3 is going back to that omega square r cube is gm. I keep repeating that too many times, but that's exactly the same argument. Okay, so why are we excited about it? I think I'm going to finish very soon. So we are excited because this is the scenario we are going to probe. I told you about the dynamical friction. When the galaxies merge, the black holes will come very close to a parsec or something due to something called dynamical friction, thanks to Chandrasekhar. It's because of the gas, because of the stars and all that. Eventually, there may be interaction of a binary disk and whatnot. Dual AGNs are quite common apparently in the early epochs, and you will bring those two black holes at the milliparsec separations, which are essentially, something like 10⁵ AU or something like that. AU is the distance between Earth and Sun. So you have to really bring that close for gravitational waves to take over. They will emit nanohertz gravitational wave, and eventually they will merge in microhertz gravitational waves, and the product is a recoiling black hole, because it's very unlikely that the black holes are going to have exactly the same masses. Unequal masses are quite likely, and there's an effect in general relativity. It's called a recoil. A linear momentum can be ejected, and such recoiling black holes should be picked up, only suggestions, by these fantastic surveys like DAISY and others. That's an exciting possibility. And of course, you have SK era PTA, LISA, and the LSST to look for various parts of this merger scenario. So in the next decade, when you guys are going to be youngsters, are going to be my age, most of these questions will be answered. And that's a fantastic, possibility, isn't it? So that's the game. And everywhere you look, there's an astrophysics there, which people have speculated. But now we will have observational data to verify that. And that's exciting. And lots of theories are required. But that's not yet that, a bit more. So we have, so you think that's there's a possibility. So in the coming decades, we are going to send missions to planets. Okay? And we are going to monitor them, these planets. I'll be done pretty much. And so we are going to, and so it's called a Doppler tracking, and the big telescopes are required for that. So for example, Cassini and things like that, you can look for YouTube videos, beautiful videos out there. So the mission to Jupiter and Saturn, this return time are of the order of, few thousand seconds. Okay? So you send the signal, you get from the spacecraft and back. And in places like Bremen, and there are lots of people working on it. My friends and colleagues they're all senior people, but they are in German, so So the idea is to search for this Doppler tracking data for gravitational wave signature. I'm not going to derive this, but essentially PTA works because somebody adapted these papers. Ellingson Downs is essentially based on this paper. That's required. So, in the case of PTA, you only get one-way signal. You don't send something, get something. So essentially the same argument. It's a beautiful paper. And this is the geometry. I'm not going to go into the details, but this is a fantastic review. I hope I will be able to work it out when I retire or something. Too many things. So, okay. So this is the emitter and this is the receiver. We get it back. So that's the, you know what this is, right? Okay. And so important thing is that any gravitational wave, even shorter than kind of distance I'm talking about will have 3 contributions. It has been worked out. So I'm not going into the details, but you can do this, and you can see that, just like the one I showed you, it's easy to kind of work it out. You find periodic terms, which goes like that. The capital T is this T prime emitted by the receiver, and things like that. So the sensitivity in the coming decades, I think our colleagues in China are doing it, both ESA and NASA has missions, so should be possible to get H of the order of that number at the frequencies which are inverse of 1,000 seconds. Not bad. We don't know whether there will be any. So that's it. I'm going to. So the multi-messenger gravitational astronomy with terrestrial, solar system, and galaxy-based gravitational observatories are going to revolutionize astronomy, astrophysics, theoretical physics in the coming years. And not even that, people are now seriously talking about creating a gravitational wave observatory like a LIGO in Moon. So this is from a young friend of mine, Karan Jani's. This is a nice paper. They even have funding for those, at least initial concepts. So, and Suvadi will talk about another observatory. I will not call it an observatory, but it's still going to revolutionize, cosmology and astrophysics, and cosmology and theoretical physics. And I'm not going to take any thunder from that. It's an amazing opportunity. We had a setback when we were, slightly young, but we will talk about all that. That's it. Thank you very much, and I will be happy to take questions.
Thank you for this very interesting talk. Questions? There are already a few in between, but now it's open for more open discussions.
Yeah.
The online part.
Could you remind me what the last parsec problem is?
I'm sorry?
Could you remind me what the last parsec problem is?
Okay. So the game is that astrophysically, maybe I can go into that slide. Well, it's I have some slides from summer, if I go and look into. So, well, it's a problem created by Martin Rees. So I don't know if it's a real problem, but it may be. So the game is that, so the argument is the following. We know astrophysical mechanism that can bring in 2 black holes surrounded by astrophysical, phenomena like gas or stars up to a parsec. Okay, and then this classic paper by Blanford, Martin, and one more. I forgot. No, anyway, I can argue that the black hole will become, will be essentially isolated at the parsec level. Separation is parsec. Black holes will become just isolated, and they can go on around each other. They're bound, and they are going to be like that forever because the gravitational waves are not sufficient to kind of bring them closer to merge in a Hubble's time. You just use the quadrupolar formula. That's what they did. So this, dynamical friction up to here, these guys are not going to come closer. They may have an accretion disk, but that's it. The separation is such that there are no physical effects which can bring them further closer. Maybe the chances are they go further. So this was considered as a major headache. So there are various ways to take care of this, in the sense that if you can bring in another guy, another black hole, so it's a 3-body effects. Finally, 2 guys can come closer, the guy gets ejected and all that, which can explain so-called the recoiling black hole scenarios. Anyway, so we don't know whether, is there. So for example, we are seeing, if you think the background we are seeing from the PTA results are due to nanohertz gravitational waves from supermassive binary black hole, there are no final parsec problem because we are seeing at kind of milliparsec separation.
But you don't know if it's from supermassive black holes.
That's true, but hopefully we can tell you that in a year's time. So
maybe just one thing to add here.
Yeah, please.
So It's true that dynamical friction plays a major role in taking away the orbital energy from the system. Dynamical friction is very important in the gas-driven scenarios. But when you fall in, you also have stellar collisions. You also have viscous drag. So that was not known back in the early days. Now from simulations, as I was mentioning, there are other mechanisms to take away energy. So the problem is no more really a problem because now we have other things to take away the orbital energy faster than the emission of gravitational waves. So I would still argue that astrophysical sources are definitely one of the very potential candidates to bring the sources nearby enough, sub 10⁻³ parsec, for them to emit gravitational waves in nano.
So it's not really an answer to final parsec problem, but recently Hamza Padmanabhan and Avi Loeb kind of pointed out that in the JWST era, they are actually seeing dual AGNs. They are binary black holes in the sense that it's a bound, and they are both visible to JWST as active galactic nuclei. So it's not easy to create that, and the fraction in the early universe is substantially larger than what we actually have, which is a fraction, few percent. They're talking about 30%. So other astrophysical sources can make the black holes come to the regime where the gravitational wave is good enough to merge. That's the so-called final. But the paper by Martin and Roger was beautiful. I mean, they have this diagram, just like the angular momentum thing I showed. They have similar one show that there has to be a way to, bring in the angular momentum, take away the angular momentum. It can come closer.
Thanks. Any more questions or comments? You have a few more. Yeah, sure.
For us, it might be more exciting if it weren't supermassive black holes.
I'm sorry? Non-super.
For us, it would be more exciting if it weren't supermassive black holes.
So that's the reason I give such a detail of what are the sources Lisa is expected to see, because I think I think there's a precedence here. When I was young, we were talking about gravitational waves that LIGO will see are 10 solar mass black holes. I have not seen many 10 solar mass black holes. We are all seeing 30 solar mass black holes, right? I mean, so it's called, so that's also exciting from an astrophysical point of view. So unexpected sources, I will say first LIGO even is highly unexpected. I mean, from standard consideration like the, final parsec problem. In the sense of standards. So yeah, so therefore, there are reasons why we saw that and all that. I'm not getting into that. Yes, but unexpected sources will be there for LISA. There's no doubt about it. And cosmic string, we have constraints, but that's another possibility. Individual, all those things. I mean, we don't know what's going to, so that's exciting. So I said, to me, LISA is going to be the JWST of Gravitational Wave Observatory. SKA PTA will come closer, but not maybe Hubble. Yeah.
My quick comment to you will be, it will be very challenging to rule out astrophysical signature. That will be the first day.
No, but we should not discourage you. So I want to be very clear about it. So yeah.
So I have a very basic question. So you were talking about many binaries, neutron star, white dwarfs, and black holes. So my question is that, so from this gravitational wave signal, can we just say about individual masses involving in the binary, or do I need extra information from its electromagnetic part?
Good question. So I didn't go into that, but I can show you one formula that will, so gravitational waves, if you're looking for the in-spiral signals, that's clean for the time being. I get, the in-spiral track you might have seen, right? That can be fitted with this formula, df by dt, as a function of the frequency. So it's called time frequency map. What I'm going to just extract from that plot is called the chirp mass. It's just a combination of individual masses. That's the quantity I can measure very, very precisely for the time being, and LISA is also going to do that. But I can, general relativity gives corrections to this, and that involves mass ratio, spin, many other things. And therefore, I should be able to get, the mass ratio, and then which is m1 over m2. This is a combination of m1 and m2. Therefore, I should be able to get individual masses. Okay. And LISA is much more exciting because it gets 2 amplitude, at 3 configurations. So I get the inclination, because inclination kind of plays a spoil spot in many of these estimates about the distance and degeneracies and all that. So that's where LISA is exciting.
Okay.
Now, if you are asking me, are they going to be as precise as the binary pulsar, especially in SKA, that will be difficult because after all, we have only one observable here, combination, but it's essentially, whereas in the case of binary pulsar timing, you actually have, many, many delays, Romer, advance of periastron variation, Einstein delay, then you have Shapiro, and if you see both the pulsars, and so it's and the effect of deep, PB dot and all that. So accuracy of those parameters will be, but once you have a system which can be seen in either LISA, LILA, and advanced LIGO, things are going to be very different. So yeah.
Okay. So actually, my concern is about the old neutron stars where the thermal radiations are not very much. So then I think it would be very difficult to resolve those individual masses. So that's why I'm asking.
No, it should still be fairly accurate. So LISA will see many galactic binaries.
Okay.
And as I showed you that, are you working with Nirmal?
Sorry?
Are you working with Nirmal or somebody like?
No.
No, that's the interest was. So let me show. Yeah, so here you can see, as I told you, so this is but this entire, there may be many sources here, which are all going to be binaries which can emit in millihertz in the galaxy.
Okay.
So there can be old neutron star binary which are not radioactive, active in radio frequencies, not radioactive the other way. So you will see them. And there's no need for them to be hot by any means. They can be very cold. And if they are eccentric, it will be exciting because then I can get the mass and mass ratio and all that. I can talk about that separately.
Okay.
Can I make a comment on the answer to his question?
Sure.
So, because, I'm talking now about LIGO, but LISA is the same thing. If we are talking for a burst, for a transient source, then of course you can identify the mass because you have the waveforms. If you talk about the stochastic background, that was the title of your slide there, then you use different astrophysical models.
Okay.
So you test your astrophysical model, which is going to give you some kind of distribution for the masses, for the spins. The spins are not so important, the masses basically. So then you have to see how different astrophysical models can give it a kind of a different modification to the spectrum that you are going to get, depending on the result that you will have once you detect the background, you know which astrophysical model is correct, which means again which mass. So depending if you are looking for transient or for the background.
Yeah, but he's asking for individual.
The same thing, but the same thing is LIGO. There's no difference between LISA and LIGO about that.
Combination rather than the individual.
Sure, but depending if you're looking for transient, then you will find the mass as we do it now. But if you want for the background, then you test different models.
Individual masses are going to be tough. You can see that will require chirping, and many of the old neutron star binaries in our galaxy, you can show that during the mission of LISA, it will not move from one bin to another.
I see.
So there is no df by dt. But there are ways to still extract the total mass and things like that. We can chit-chat about it.
One simple way to think about it is that how many and how heavy. You can have how many sources of what masses we do not know. So you cannot break the degeneracy by just seeing one number of stochastic background amplitude. Okay. In individual events, you have the oscillations and the phase evolution, which gives you the masses.
Yeah, but unfortunately, phase evolution may not be there. That's right.
So because you do not measure something in power, you lose the phase, and you have many of them. So you do not know few lighter, few heavier, or too many lighter. It's always a degeneracy.
I see.
We can chit chat.
Okay.
Catch me.
In the break.
Any more questions before we go break for coffee? Of course, you can ask him later as well. I do not see any more hand ups, so let's thank Gopu again for the very nice talks, and see you at 11:30. Thank you.